name is Jürgen.
And my name is Patrick.
We wanted to have a question about electromagnetism.
And our aim of this project was that we wanted to investigate how you can make electricity via a magnet and a conductor. We also wanted to know about how you can use electromagnetism in our everyday life. Another thing that we wanted to know about was expansions of electromagnetism. For example, how can we use it to transport electricity? And as the last thing, we wanted to know about different machines that make electricity.
So, who discovered electromagnetic induction?
Well, that was Michael Faraday and Joseph Henry in 1831. But what is electromagnetic induction?
Electromagnetic induction is when you create electricity with a magnet and a conductor. But what is a conductor?
Well, a conductor is a conductive metal. It normally lies in a transitional metals group that could be, for example, iron or copper.
How do we make electricity with a magnet and a conductor?
Well, first of all, we're going to take a magnet and a conductor. We're going to put them as close together as possible, and we're going to make the magnet spin. This way we will create electricity. But how do we reach that level of voltage?
When you make electricity, you will have a voltage. It can be measured in a galvanometer. There's three ways to make a high voltage. The first one is the more current you have on the conductor, the higher voltage you reach.
The second one is that the closer the magnet is to the conductor, the more electricity you'll make.
The third one is the quicker the electromagnetic wave field changes, the higher voltage you reach. By following these steps, you will gain a higher voltage.
Okay, so now we're going to talk about Hans Christian Ørsted. First of all, he was the first one to observe electromagnetism. He worked at a pharmacy with his father, and was also here he got his interest into science. Ørsted had a brother named Anders, and they were self-studying at home in their younger years. Though in 1739, Anders and Ørsted made their way into the University of Copenhagen. And in 1769, Ørsted made some papers in physics, and he was awarded a great honor for these papers. At the April 21st, 1820, Ørsted noticed that a compass that wasn't facing north when an electric current from a battery was on. Though when the current was off, the compass was facing north again. With this and further investigation, he noticed that magnetism and electricity has something to do with each other.
Okay, so I'm going to talk about Michael Faraday. Michael Faraday was born in Newton, but the 22nd September 1791. He passed away at Hampton Court the 25th August 1867. He got buried at Highgate Cemetery. Michael Faraday was a British scientist. He was one of the most influential scientists in electromagnetic induction. For example, one of his discoveries was he could affect small rays of light by using magnetism. The 26th of December, Michael Faraday described his discovery of the first dynamo. Later in the year of 1832, at Oxford University, granted Faraday a Doctor of Civil Law degree. This was a great honor for Faraday. During the war in 1853 to 1856, the British government asked Michael Faraday for advice for production of chemical weapons, but due to ethical reasons, Michael Faraday refused to participate in the war. When we burn stuff like tree and coal, you will release energy as heat. You can see here we're using the water we're boiling to make steam, and steam will ascend into this pipe into a steam turbine. This steam turbine is connected to a generator which produces electricity, and the electricity will be transported into the substation / transporter where it out.
Okay, so now we're going to talk a bit about transformers. Transformers are built out of the concept of electromagnetism. To build one, you'll need a primary and a secondary coil. In this experiment, we used the blue one here as a primary coil of 200 turns, and the second one here, yellow one, 400 turns as our secondary core. When we do this, we're making a step-up transformer. The electricity will go into the primary core, and we can connect in the secondary core to, for example, a light bulb. If we turn them around and say we use the yellow one as our primary core and the blue one as our secondary core, then we'll have a step-down transformer. But how can we use this, you might ask? Well, it's quite simple. Home in your sockets, there's too high voltage, for example, to charge your computer or cell phone. This is why you'll have a step-down transformer along the wire. For this, you will ensure that you don't burn off your computer with too high voltage.
Okay. If you ever imagine that one of the most common machines in the Danish nature is an electromagnetic induction machine, because the windmill is actually an electromagnetic induction machine. When we have an electromagnetic induction machine, we need a rotation. And the rotation of the machine is the wings, which tells us there has to be a magnet connected somehow to the wings. And it's placed in the head. One of the good things with the windmills is that they don't require a huge amount of space. You can have it almost any place you want to. But the windmills don't make this huge amount of electricity as a, for example, a nuclear reactor. That's why the big countries don't use them as the main source of electricity. If you take off the roof of a windmill, we'll see a generator, which is somehow connected to the wings. And its generator is what we're showing you here. This is a conductor. We are connecting the conductor to the ammeter. And when we're doing this, we will we'll take a magnet, insert it here, and move it. This will produce electricity, and it's electromagnetic induction.
A bit about electromagnetism in our everyday life. When you're making electricity via electromagnetism, you're having a magnet move very close to a conductor. But what happens if you take a magnet surrounded by a conductor and put electricity to the conductor? The answer is quite simple. You will make the magnet move. When a magnetic field is changing, the magnetic field will move depending on the magnet. Though if the magnetic field isn't moving, the electrical field from the conductor will take effect over the magnetic field and make the magnet start to move.
By using this, you can make a thing rotate completely without CO2 carbon dioxide released. And I'm going to explain how now. First, you need a power source that can make the magnet rotate. It could be a river, it could be the wind, it could be your own body. Then you need a conductor that surrounds the magnet that just stays close to it. Then you will create electricity, which will transport with a high voltage using a transformer. The electricity will reach your destination in no time. There you have a magnet surrounded by conductors. The conductors will be electrified, creating an electric field. The electric field will affect the magnet's magnetic field and will make the magnet move with a frequency. And congratulations, you have created your own carbon dioxide free rotating magnet. We're using this right now as transport. Maybe some of you got an electric car, but I don't think it's more than 50% of you. I guess some of you have a dynamic light on your bikes. That's also electromagnetic induction. The rotation is created by standing the pedals. The magnet is placed on a wheel. The conductor is placed on a wheel too, but there's a small amount of space between the wheel and the conductor, so the magnet can pass without being blocked. And the electricity that's been made is used to light up the light bulb. Okay, if you don't know what this is, I would like to tell you. It's a magnetic field's waves. It shows us the concentration of electrons in the area. The higher the waves are, the bigger concentration. The volts in this diagram is called electron volts. Electromagnetic waves have crests and troughs, similar to those of the ocean. The distance between the crests are the wavelength. The shortest wavelengths are just fractions of the size of an atom. The longest wavelengths that have been the scientists currently have calculated can be larger than the diameter of our planet. Frequency. Frequency is the number of crystals that pass the point you have given within a second. This will be described as the frequency of the wave. 1 wave per second, or cycle per second, will be presented as a hertz. As an example, 2 cycles has passed a given point within a second. This will be presented as 2 hertz.
We've had a very great time working with this experiment. We've learned a lot of things, and here are some of them just now. We've learned a lot about electromagnetism in special. We've learned to make our own coil, which we've shown presented right here. We've learned a lot about some great scientists, for example, Hans Christian Ørsted and Michael Faraday. We've learned how to spread current, also learned how to work under pressure.
I would like to say thank you to Patrick's big sister, Simone, for helping us making grammar corrections, Patrick's mom for making us work more, Patrick's dad for helping us with the board and paying for the spray paint and the copper wire, my mom for making me work in a more effective way, my stepdad, Tom, for learning us a whole bunch of knowledge about the subject. And last, I would like to say thank you to Luciana for supporting us and believing in us as a team.